In this section, we're talking about confidence intervals, but this time we're talking about confidence intervals for quantitative data. So before we jump in, let's just review how this works for categorical data. So say we talk to people and we ask them if they had a dog. And so their response is either going to be yes, they have a dog, or no, they don't. And so if our sample has 100 people in it, we might get a sample proportion of 0.45, meaning that 45% of those 100 people had a dog. And from that, we could figure out the standard error of p hat, which is the square root of p hat times 1 minus p hat over n. Now, in this case, that would be about 0.05. And then using these numbers, we could figure out a confidence interval. So we would get a confidence interval of p hat plus or minus z times the standard error of p hat. And that z there would depend on how confident we want to be. So if we wanted to be 95% confident, we would use a z-value of 1.96. Now, for quantitative data, the formula looks quite similar, but there are some key differences. So like with the formula for proportions, we have something plus or minus something times a standard error. So the general template is very similar. Now, in this case, we would be asking a question that would elicit quantitative data, like how many dogs do you have? So now the data that they would be responding with would be quantitative data, like I have no dogs, or I have one dog, or I have two dogs, right? And so we would get a great deal of quantitative data from these questions. Now, just like before, we use n to tell us the sample size, right? So maybe in this case, we ask 100 people. But instead of getting a sample proportion like p hat, we would get a sample average like x bar. And let's say our x bar is something like 1.45 dogs on average. Now, we could figure out the standard error of x. And so the standard error of x is given by the standard deviation of our sample divided by the square root of n. So let's say I put these numbers into my calculator. I'm told that the standard deviation is 1.03. Then I would have 1.03 over the square root of 100 for my standard error. Now, here's where things get different. So, this is different from what we saw with proportions. When we're dealing with quantitative data, we have that similar formula, right? X bar plus or minus. Now we use the letter T times the standard error of X. Now, we've already talked about X bar is the average, and I just gave the formula for the standard error of X. What's different is that this T, and let's make it red to match the Z on the other side, it depends on two things. It depends on how confident you want to be, but it also depends on how big your sample is. Okay, meaning it also depends on N. Now, the first person who figured this out was actually the head brewer at the Guinness Breweries. He was an English statistician named William Gossett. I know, uh, English statistician, but Irish beer, but he was an Englishman. And he found that the distribution for quantitative data wasn't exactly normal. Okay. So we're used to any symmetric unimodal distribution. We call that normal. And so what he found was, let's say this is the normal distribution. If he took a sample of quantitative data, he didn't get exactly that normal distribution. He would get something that would be a little lower on the outside and then a little pointier in the middle. Okay, something like this. And maybe that was for when his sample was 100. And the smaller the sample was, the pointier the distribution got. And so he called these t distributions. Now, the moral of this story is that if we want to figure out one of these confidence intervals, we have to use our calculator in this case because these depend on both the confidence level we're interested and the sample size or n. And so because it depends on both of those, your calculator can take both of those into effect. So in the next video, you're going to see how to do this on your graphing calculator.